Hello, welcome back to this series of lectures on numerical optimization. In the last class, we started discussing about constraint optimization problems, and in particular, we were looking at a problem of this type, where we want to minimize an objective function f of x subject to the constraint that every variable belongs to the set x. So, this set x is a feasible set or a constraint set, and this is the objective function, and we are interested in giving some algorithm which is an iterative algorithm that generates a sequence x k which converges to a local minimum of this problem. So, a conceptual constraint minimization algorithm would look like this, that given x 0 which is feasible and setting the iteration counter to 0, we continue the algorithm till the stopping condition is satisfied at x k, and at every step of the algorithm what we do is that find x k plus 1 in the feasible set x, such that the value of the objective function at that point x k plus 1 is less than the value of the objective function at the current point, and then we increase the iteration counter and the process is repeated. And finally, at the end, when the algorithm terminates, we get a local minimum of f x over the set x, which is a feasible set. So, this is one of the solutions of this this problem. Now, what we are interested in is that what is the stopping condition that needs to be satisfied at x k. If you recall, for an unconstrained problem, we chose the stopping condition to be the norm of the gradient to be less than some epsilon, but that condition cannot be directly used for a constraint problem, because the gradient of the objective function may not vanish at a local minimum of a constraint problem. So, we need to come up with a different condition which can be used as a stopping criteria for this algorithm, and later on we will find see different ways of finding x k plus 1 belonging to the feasible set, such that the value of the objective function decreases. Okay, so let us start looking at this stopping condition that needs to be satisfied at a local minimum. So, consider this problem and recall the definition of strict local minimum that we discussed in the last class. So, if x star is a strict local minimum, if there exists some epsilon which is a positive quantity, such that in the neighborhood of in the epsilon neighborhood of x star in the set x, the value of the objective function f of x star is strictly less than the value of f x for every x in the neighborhood, where x is not equal to x star. So, at a local minimum of a constraint minimization problem, you can see that the function does not decrease locally by moving along the directions which contain feasible point. So, suppose we want to minimize a function. So, suppose that this is an interval that we are looking at, and the function is one dimensional, and suppose the function is something like this. So, we saw in the last class that this point A is a local minimum, then this point is also a local minimum. So, if we consider this point is also a local minimum, and this point is also a local minimum in addition to the point A. So, we saw that these are local minima, and this point is a strict local minimum, while this point is not a strict local minimum, because if you see that in the neighborhood the function is constant. So, if you consider this point, and this is going to be our feasible region. So, our feasible region is the closed interval a b, so which is denoted here by this portion. So, this is our feasible region. So, if we move along the feasible region from the point A, the function strictly increases. Same is true here. So, if we move either from this point, if we move either in the increasing direction of x or in the decreasing direction of x, the function value strictly increases. So, and if you look at this point, then in the neighborhood of this point, if we move, the function at least does not decrease. Okay. So, what we are interested in is finding out those points in whose neighborhood, if we make a movement in the feasible set, the function at least does not decrease. So, in other words, we are at a local minimum of a constraint minimization problem, the function does not decrease locally by moving along directions which contain feasible points. Now, this is a statement which describes a local minimum. Now, how do we convert this statement into algebraic condition? Okay, so that is what we want to see. So, consider the same problem, and let us define a set of feasible directions. So, a non-zero vector d in Rn is said to be a feasible direction at point x belong to the set x if there exists some delta 1 which is a positive quantity, such that x plus alpha d belongs to the set x for all alpha in the range 0 to delta 1. Note that we are not considering d equal to 0, because we are assuming that x always belongs to the set x. So, we are considering all those points which are feasible, and therefore, if we take d equal to 0, that is a trivial, this condition is trivially satisfied. So, we will not consider d equal to 0 in this case. So, we are interested in finding those directions d such that x plus alpha d belongs to the set x for some alpha in the range 0 to delta 1, where delta 1 is a positive quantity. Now, let us see this definition. So, if we have a constraint set x to be a set like this, and let us consider a point so let us say that this point is x a. So, at x a we are interested in finding out what are the feasible directions. So, you would see that some feasible directions are like this. So, if we make a small movement along these directions, we still retain feasibility of the set. On the other hand, suppose if we take this point and then we can move in any direction in the neighborhood. So, these are all some of the feasible directions that we have drawn here. So, from this point, if you consider the point x a, we cannot move in the direction in the other directions, because then we will not retain feasibility. While if we consider the point x b, locally we can move along any direction in the input space and we still remain feasible. Now, let us consider another example. So, let us consider another x which is like this. Now, let us consider a point, some point, let us call it as x c. So, you will see that one can move along these lines. If you consider a point x d, one could move along. So, what is drawn here is only some set of feasible directions, and likewise we can draw feasible directions for a given set. Now, let us consider another example. So, let us assume that our set X is a circle. So, let me call this as x1 and this is x2. So, x is equal to set of all x1, x2 such that x1 square plus x2 square equal to 1. So, this is a circle of radius 1 which is drawn here, and so let us take a point. So, let us call this point as x e, and now suppose we want to find out what are the feasible directions at x e which belongs to the set x. Then you will see that we cannot find a straight line direction which is feasible from the point x e, but what we can do is that we can form we can get what are called the curvilinear directions. So, if we move along these curves we can retain feasibility, but these are not the straight line directions. So, what we are interested in is getting the straight line directions d such that x plus alpha d belongs to the set x for sufficiently small alpha positive alpha. So, we will not be interested in the directions like this. Now, remember that in this example what we have considered is only a set of directions, or what are indicated here are only a subset of the directions which are possible at a given feasible point. Now, how do we get all possible feasible directions and then show them algebraically? Because this is one way to show the directions geometrically, but then how do we represent these directions algebraically? That is what we want to see. So, let f of x, the script f x, denote the set of feasible directions at x belong to the feasible set x. So, remember that the feasible directions are always associated with the feasible set x. So, for a given feasible set x and a given point x which belongs to that feasible set x, we can denote the set of feasible directions by f x. Now, if you recall the definition of a local minimum, in addition to the feasible directions, we need those directions along which if we make a movement, we can decrease the objective function. So, those directions are called descent directions, and we have seen these descent directions when we studied unconstrained optimization problems. So, a non-zero vector d in Rn is said to be a descent direction at x if there exists delta 2 which is a positive quantity such that f of x plus alpha d is less than f x for all alpha in the range 0 to delta 2. So, note that the descent direction is always associated with the objective function, while in the definition of feasible directions you will not see any mention of the objective functions, because the feasible directions are always associated with a constraint set and the descent directions are always associated with the objective function which is to be optimized. In this case, we want to minimize this objective function f of x. So, the descent direction is associated with f. So, let us denote by script d and the set of feasible directions at x belongs to x, and as I said that the descent directions are always with respect to some objective function f. Now, we have seen that the contours of a typical objective function would look like this. These are the contours of the objective function. Now, let us assume that the objective function is differentiable. So, at a given point, let us take a point and let us call this as x a. So, let us call this as x a. Now, if the function is differentiable, we can find out the gradient of the function, and let us assume that the gradient of the function is pointing in this direction. Now, we have seen earlier when we studied unconstrained optimization that the gradient points in the direction where the function increases. So, along this direction the function decreases. Now, we also saw earlier when we studied unconstrained optimization problems that if we take a tangent plane, so this is orthonormal to the direction. Then, so if we look at this set of all directions which make an obtuse angle with gradient of f at x a. So, if we make a movement along those directions, then the function value decreases. So, those are the descent directions, and we have seen this earlier. So, now let us try to put these conditions in algebraic form. Now, to start with, let us consider a problem where we want to minimize the function f of x subject to the inequality constraint of the type h j x less than or equal to 0 and the equality constraints of the type e I x equal to 0, where x is any vector in n dimensional space. And let us consider the feasible set x defined using the constraints. And as we mentioned earlier that at a local minimum x star of x, the function does not decrease by moving along feasible directions. So, let us consider this problem, and so we have a theorem which characterizes a local minimum of this problem. So, if x is a non-empty set in R n and x star belonging to x the feasible region is a local minimum of f over x, then the set of feasible directions and the set of descent directions, they have empty intersection. So, this is a very important result, and this gives the necessary condition for the local minimum of a given constraint optimization problem. So, let us look at the proof of this theorem. So, let us assume that x star is feasible and is a local minimum. Now, the proof will be given by method of contradiction, and for that we assume that there exists a non-zero D such that that lies in the intersection of f x star and d x star. Okay. So, let us assume that such a D exists, and that therefore, this set f x star intersection d x star is non-empty. Now, since D belongs to f x star, the set of feasible directions, so by the definition of the set of feasible directions, we can say that there exists delta 1 greater than 0, such that x star plus alpha D belongs to the set X for all alpha in the range 0 to delta 1. And similarly, one can use the definition of d x star to say that there exists delta 2 greater than 0, such that f of x star plus alpha D is less than f of x star for all alpha in the range 0 to delta 2. So, there exists delta 1 such that the direction D is feasible, and there exists delta 2 such that the direction D is also a descent direction. Now, if you take a minimum of delta 1 and delta 2, then you can see that along the direction D, as long as alpha is in the range 0 to minimum of delta 1 and delta 2, x star plus alpha D always belongs to x, and f of x star plus alpha D is less than f of x star. So, that means that there exists x in the neighborhood of alpha neighborhood of x star, and which is in we intersect that alpha neighborhood with x such that f of x is less than f of x star for every alpha in the range 0 to minimum of delta 1 and delta 2. And so, that means that in the local neighborhood of x star, we are able to find some x which is not equal to x star, such that the value of the function at x is strictly less than the value of the function at f of x star, and that contradicts the fact that x star is a local minimum, and therefore, because of this contradiction, we cannot have a direction D which is in the intersection of the feasible set and the descent set if x star is a local minimum. So, this contradicts our assumption that x star is a local minimum. Now, first let us look at the way of characterizing the set of descent directions, and as I mentioned earlier that if we assume that the function is sufficiently smooth, then the set of descent directions can be characterized using the gradient of the objective function. So, let us consider any x in the feasible set X and assume that f is in C2. In fact, for our current analysis, we do not need f to be in the class of C2 functions. We just need class of f belongs to C1, that is the class of continuously differentiable functions. But later on, when we move on to the second order condition, we will need this condition. So, I have assumed that f is in the class of twice continuously differentiable functions. Now, we already know by the definition of directional derivative that gradient f x transpose D is nothing but limit as alpha tends to 0 from the positive side f of x plus alpha D minus f x by alpha. So, if this quantity is less than 0, then we can say that in the neighborhood of x where alpha is greater than 0 in a sufficiently small neighborhood of x, this numerator will be less than 0. So, that is gradient f x transpose d less than 0, it implies f of x plus alpha d less than f x. And this means that so this will be true for sufficiently small positive alpha, and therefore, we can say that d is a descent direction, and therefore, we can say that d belongs to the set dx. So, if we are able to find a direction d such that the direction d makes an obtuse angle with gradient f x, then we can say that d is a descent direction. So, let us define a set d tilde to be the set of all directions d such that those directions make an acute angle with gradient of f of x. So, clearly d tilde x is a subset of dx, and therefore, we can say that x star is a local minimum if f of x star intersection d tilde x star is a null set, or they have empty intersection. And as I mentioned earlier that so, if we look at this figure, then this open cone of directions, these are the directions, the set of D such that gradient f of x a transpose D is less than 0. So, this open cone gives us the set of descent directions at x a for the function f. So, if you make a movement along any direction in this cone, that will be a descent direction. Okay. So, d tilde x is a way to characterize dx in terms of the gradient of the function. So, we were able to convert the dx in the original condition by d tilde x, as d tilde x is a subset of dx, and moreover d tilde x can be written in terms of the gradient of f at a given point x. Now, so if we consider f of x star to be R n, that means that every direction in R n is locally feasible, then x star belong to x is a local minimum. That implies that this set has to vanish, because if this set is R n, then the d tilde x star should x star belong to x is a local minimum implies that d tilde x star should be a null set, and that is the set of all d such that gradient f x star transpose d is less than 0 is a null set, and this will be possible when gradient f x star is a 0 vector. And this condition conforms with our unconstrained optimization optimization problems, where we discussed about the local minima of unconstrained optimization problems. So, there we saw that x star is a local minimum implies that gradient f x star is equal to 0. So, so we have seen one way to characterize the set dx star. Now, how do we characterize f of x star algebraically for a given constraint set x, and that is what we will see now. So, for the time being, let us assume that we are interested in solving this problem where we want to minimize f of x. subject to only the inequality constraints of the type Hj(x) less than or equal to 0, and there are L such inequalities, and x is a point in n dimensional space of real numbers. Now, again we assume that f and Hj's belong to C2, although for the present analysis it is enough that f and Hj belong to C1, but later on as I mentioned earlier that we will need twice continuous differentiability. So, we will assume that the functions are twice continuously differentiable. Now, so let us denote x by the set of all Hjx less than or equal to 0, j going from 1 to L. Now, let us consider a constraint set that we saw earlier, the set x. Suppose the set x is so, this is the set x. Now, let us consider a point now this constraint set is made up of say 3 inequalities which are shown here. So, one inequality is denoted using this, the other is denoted using this, and then the third one is denoted using the green color. So, we have 3 inequalities which were used to form this constraint set, and if we look at a point x a, you will see that the only 2 constraints are used to represent the point x a. So, this third constraint, even if we perturbed a little bit, that is not going to change the representation of the point x a. So, in this case these 2 constraints are said to be active constraints as far as the point x a is concerned. So, if let us number these constraints. So, let us call this as 1, this is 2 and this is 3. So, at x a the constraints 1 and 3 are active. Now, if we take a point, so let us take another point x b, which is also a feasible point. So, at the point x b the constraint 2 is active. So, even if we move the constraints 1 and 3 a little bit, the point x b is not affected by a slight perturbation of the constraints 1 and 3. And if we consider a point x c, so let us consider a point x c which is in the interior of the set. Now, you will see that this point at this point x c no constraints are active. That means that even if we perturbed any of these constraints a little bit, the point x c still remains feasible and does not get affected. So, at a given point, feasible point, when we want to characterize the set x, the feasible set algebraically, or when we want to characterize the set of feasible directions at x a for the feasible set x algebraically, what we have to do is that we just have to consider what are called active constraints. Sometimes they are also called binding constraints. So, if we consider another example, so suppose if we have a feasible set x, and let us number the constraints. So, we have 5, inequality constraints, and the set is found using the intersection of those 5 inequality constraints. And if we consider a point, so let us call this point as x d, you will see that only the constraints 1 and 2 are active, while if we consider a point x e, only the constraint 4 is active as far as the point x is concerned, and in the interior, if you consider the point x f, no constraints are active. Or in other words, we can define active constraints as those constraints which are satisfied at a given point with equality. So, if you look at x a, the constraints at 1 and 3 are satisfied with equality. At x d, the constraints 1 and 2 are satisfied with equality, and all the other constraints are inactive, the constraints 3, 4 and 5, because they are not satisfied with equality sign. And similarly, at x f, none of the constraints is active, as the point x f satisfies these constraints with strict inequality. So, let us define the set of active constraints A x to be the set of all j's such that h j x equal to 0. So, the set of all constraints which are satisfied with equality. Now, here is an interesting result, that for any feasible x, if we define f tilde x to be the set of all directions d such that gradient h j x transpose d less than 0, that means that the directions which make an obtuse angle with the gradient h j x for all j in the set A x, the set of active constraints. So, if we collect all the active constraints and find out the set D, the set of directions which make an obtuse angle with all the gradients of the active constraints. So, let us denote that set by f tilde x, and the result says that this f tilde x is a subset of f of x, or is a set of all feasible directions at x. Now, the important thing about this result is that now we are able to get a set in terms of the gradient of the active constraints, and that set turns out to be a subset of f x, and this set f tilde x will be useful for writing our optimality condition. Okay. So, let us look at the proof of this lemma. So, the claim is that f tilde x is a subset of f of x. Now, what we have to show is that if we take any vector d which is in f tilde x, that vector d is also in the set f of x. So, let f tilde x be non-empty, so that there exists some direction, non-zero direction d, such that d is in f tilde x. Now, since that is since gradient h x transpose d is less than 0, that is d makes an obtuse angle with all the gradients of the active constraints, we know that d is a descent direction for the function h j, where j belongs to a x. We have seen this result when we talked about the objective function. So, similar result holds here, that d is a descent direction for the function h j, or in other words, there exists some delta 1 greater than 0 such that h j of x plus alpha d is less than h j x for all j in the set of active constraints at x. And we know that since j belongs to a x, h j x equal to 0. That means that h j of x plus alpha d is less than 0, which means that D is also a feasible direction. Now, if we consider all the all the constraints which are not active at the current point x, for them we can write that there exists some delta 3 greater than 0 such that Hj of x plus alpha d is less than 0 for all alpha in the range 0 to delta 3 and j not in the set of active constraints. So, for the set of active constraints we were able to find a direction d or we were able to find delta 1 such that Hj of x plus alpha d is feasible, and for those constraints which are not active we were able to find delta 3 such that Hj of x plus alpha d is less than 0. Now, if we take a minimum of delta 1 and delta 3, then we can see that Hj of x plus alpha d is less than 0, which means that it belongs to the feasible set. So, x plus alpha d belongs to the feasible set x for all alpha in the range 0 to minimum of delta 1 and delta 3, and that means that d is a feasible direction, because by definition we have found some delta 2 which is greater than 0 such that x plus alpha d is a feasible point for all alpha in the range 0 to delta 2, and delta 2 is nothing but mean of delta 1 and delta 3. So, this important lemma lets us characterize a feasible set by using the gradients of active constraints at a given point, at a given feasible point. Now, we can now combine these results which we saw earlier. So, let us denote the constraint set by the set capital X, and for any feasible point x in the feasible set, we have already defined f tilde x to be the set of all the directions d such that those directions d make an obtuse angle with the gradients of the active constraints, and that f tilde x is a subset of f x, and similarly d tilde x we defined it to be set of all directions d which make an obtuse angle with gradient f x, and that is a subset of the set of descent directions, and this gives us an important result. And we saw earlier that x star in the feasible set is a local minimum, implies f x star, the feasible set at x star, and the set of descent directions at x star, they have a empty intersection, and since f tilde x is a subset of f x, d tilde x is a subset of d x, we can write this as the condition where the sets f tilde x star and the sets d tilde x star, they have a empty intersection, because f tilde is a subset of f and d tilde is a subset of d. Now, the reason for doing this is that this condition is written in terms of the gradient of the objective function and the gradients of the active constraints, and so it can be written in algebraic form. So, this is the result that we are interested in, that x star which is feasible is a local minimum, implies that f tilde x star intersection d tilde x star is a null set. Now, remember that this is only a necessary condition for local minimum, because we will see later that there could be situations where f tilde x star is a null set or d tilde x star is a null set, and which will automatically mean that this set is a null set, but that may not mean that x star is a local minimum. So, this is just a necessary condition, and the utility of this condition depends on the constraint representation. So, this is a very important point, and we will give some examples about that. And this condition cannot be directly used for equality constraint problem if you write the equality constraint as a set of inequality constraint problem. Now, so let us look at this point first, that this is only a necessary condition. Now, suppose at a given feasible point x, the gradient of the function vanishes. So, which means that if the gradient of a function vanishes, so gradient f x is 0, then the set d tilde is a null set, and if the set d tilde is a null set, then this set f tilde x intersection d tilde x is a null set, and that does not guarantee that x is a local minimum. So, this is a very important point that needs to be remembered. Now, the utility of the condition depends on the constraint representation. So, let us look at some example. So, let us consider a problem, minimize x1 square plus x2 square subject to x1 plus x2 minus 1 cube is less than or equal to 0, x1 greater than or equal to 0, x2 greater than or equal to 0. Now, if we consider the feasible region, so we have x1 and x2 along the axis, and so this constraint does mean that x1 plus x2 minus 1 has to be less than or equal to 0. So, that its cube is also less than or equal to 0. So, this constraint is represented using this, and then so this is the first constraint, and the second constraint is x1 greater than or equal to 0. So, it is this, and then the third constraint. So, together this forms the constraint set, and now if we write this function or the problem as minimize f x subject to h1 x less than or equal to 0, h2 x less than or equal to 0, and h3 x less than or equal to 0. Now, if we take any point, so let us take a point on this so let this point be x. Now, at this point, if we take gradient h x1, so let me call this point x a. So, gradient h1 x is equal to 0, because this point satisfies x1 plus x2 minus 1 equal to 0, and the gradient of this quantity with respect to that will be a 0 vector. So, once we have a 0 vector, if we start looking at the set of feasible directions at x a, and then represent them using the set that we saw earlier, so we saw that at a given point x a, the one of the gradients in fact, there was only one active constraint. So, for that active constraint the gradient is 0 and therefore, the f tilde x will be a null set, and that is clear from this figure. So, if we write f tilde x a is equal to the set of all d's such that gradient h 1 x a transpose d is less than 0, and since gradient of this remember that at x a this is the only active constraint, the first constraint is the only active constraint and this is a null set, and therefore, f tilde x a intersection d tilde x a will be a null set. But if you look at this problem formulation, so if you look at this problem formulation, what we are interested in is minimizing x 1 square plus x 2 square subject to this. So, you will see that this point, the origin, this is going to be our x star, and certainly x a is not a local minimum. But suppose if we represent this constraint, so if we consider the same problem, minimize x 1 square plus x 2 square subject to x 1 plus x 2 minus 1 less than or equal to 0 and x 1 greater than or equal to 0 and x 2 greater than or equal to 0. Now, again if we take the point x a, so this is going to be our feasible region, and if we take the point x a, so gradient h 1 x x a will be 1 1 and which is not 0. So, the same feasible region, if we represent it using a different constraint, then we get a gradient vector which is a non-zero vector, and this is unlike the previous case where we had the gradient vector to be 0. So, remember that this is a 0 vector. So, you will see that the same constraint set, if it is represented in a different way, then we could avoid the f tilde x a from not becoming a null set. So, if you write the f tilde x a here, so f tilde x a will be the set of all directions d such that gradient h 1 x a transpose d is less than 0, and this is nothing but the set of directions d such that d 1 plus d 2 is less than 0, and this set is not a null set. So, we were able to get f tilde x a which is not a null set, and clearly we know that x a is not a local minimum of this problem. Now, another important point that one has to note is that this condition cannot directly be used for equality constraint problems, and we will see that now. So, if we minimize x 1 square plus x 2 square subject to x 1 plus x 2 equal to 1, this is our equality constraint problem. Now, this problem we can write this as minimize x 1 square plus x 2 square subject to x 1 plus x 2 greater than or equal to 1 and x1 plus x2 less than or equal to 1. Now, this constraint we can write this as minus x1 plus x2 less than or equal to minus 1. So, h1x less than or equal to 0 is a given is this constraint, and h2x less than or equal to 0 is the constraint x1 plus x2 less than or equal to 1. Now, you will see that for a given feasible point, if we take the gradient h1x transpose d less than 0 and gradient h2x transpose d less than 0, that set will be a null set. So, if we write a equality constraint in this form, then we will always get f tilde x to be a null set, and so for any feasible point f tilde x becomes a null set, and that does not guarantee that x is a local minimum. Now, we will see more about this condition and how to write it in the actual algebraic form in terms of the gradients of f and then the gradients of the active constraints in the next class. Thank you.